So I kind of had a thing like this, and for t goes off to infinity, this thing as a function of the difference between omega and omega fi. This function here, this guy, the sine squared over x squared, it's got a bunch of oscillations, and then it'll be kind of really sharply peaked at around the origin. So at large times, basically the contribution to this integral will come from omegas that are close to omega fi. It'll be when we're close to on resonance. So that kind of motivated us to consider approximating this function as a delta function. And there's a factor of pi associated with the fact that the integral over delta function has to be 1. So we introduced some factor of 2 pi to sort of fix that up, the normalization. We got 2 pi, and we have this a fi squared over h bar squared, and then we have the delta omega minus omega fi, like that. So that's the idea there. So yeah, and the factor of t got canceled because we factored out a factor of t from the delta function. So yeah, so that's where we were. That's where we left off. Any questions about that? No? Okay. So this would be the transition probability. You can use this general expression with the signs if you don't care to do this approximate thing. The reason you do this approximate thing in terms of the delta function is often you want to know the rate of transitioning, not to just a single state f, but to a whole set of states per unit time. So you want to often calculate a transition rate. And some gamma, and often you're interested in a whole set of possible final states. So you want to take your probability from transitioning from I to F and sort of divide it by the time. So you'll have a rate at which you transition from some fixed initial state, whatever you prepared your system in, to any number of final states. So the idea is you might prepare your system in like a ground state, some initial state preparation, and then you perturb it in some way with a light wave or an oscillating field. And you just want to know what the rate is of transitioning away from your prepared state is. And so you would sum over like all the possible final states that you, or for instance, say you're in you create a bound state, like you bound an electron, or you put something in some kind of potential with a bound state, could be a bound electron, as I said. And then you perturb it and you ask, what's like the rate at which the electron leaves and becomes a free particle. So if you think about that, then a free particle is, of course, any kinetic energy. And so you would have to sum over all the possible final kinetic energies, for instance. So there's a set of final states that you, in principle, would be interested in. And often those have a continuous energy spectrum. So instead of summing over final states, what you would want to do is you want to integrate over all the possible energies of your final state. And then there's going to be, for those of you who've seen any solid state, this should be familiar, there will be some density of states. And this is just the number of states. It's the density of states. It's just a number of states with energies between E and E plus dE. So not per, and of course it's per dE. In other words, it's dN dE. dN is the number of states, in that band of energies between E and dE, and then you divide by dE. So when you integrate up, you would get all the states, and you need the E in there, of course, because the expression that you have for the probability will depend on E, because that'll give you that transition frequency. So the rest is the same. It's 2 pi over h bar squared. Now you see the delta function is kind of convenient because we have this integration, so the delta function will help perform the integration. So you have that. And now we can stick in, we can convert the omegas back to the energies, right? By sticking in an h bar. So we can write this as the integral from d of dE is density of states. And now we have 2 pi over h bar. We can absorb one factor of h bar into the delta function, and that will give us h bar omega, which is the energy of the perturbation. So it'd be like the energy of a photon incident on your system, thing like that. And then the omega phi is just the difference in the energy levels. So E would be the final kinetic energy, for instance. And then, of course, you start with some initial EI. So it's just the difference in the, it's a final minus initial, right? With a minus sign. So that's just that. So you get this delta function. And now you can evaluate it because we're integrating over all of the final kinetic energies, right? So now we can just evaluate this integral because, well, it's just a delta function. So this becomes 2 pi over h bar AFI squared. And now this is the density of states evaluated at the initial state plus h bar omega, which is the kind of associated energy of the perturbation that you're putting in. And this is called Fermi's Golden Rule. And it's nice because it's a general formula for calculating transition rates between, ground states, say, and free particles, bound states and free particles. So you'll do this, you'll practice this for your homework. And in recitation this week, maybe on Thursday, I'll talk about how you derive a density of states for, say, a free particle. This, you can look up how to do that in any solid state, intro solid state book. But I won't do it in class because I don't think it's particularly important. It's just counting states. You could put, it's just a particle in a box, essentially. You can put a particle in a periodic box and then count the number of wave functions that can fit in the box at a certain energy. And that's kind of it. It's not particularly interesting. I assume you've seen it at some point before. It's a very common kind of thing to do. So yeah, so I won't do it. So the density of states is typically just for a free particle. But I'll do it in recitation. And I guess since the homework is not due this week, the recitation will be Thursday. So this will be in recitation on Thursday. I'll show you how to calculate that. Okay, so now with this completed, you're actually now can do the whole, you can do all of homework too. So you could have done most of it already, but this is the very, very last bit that I needed to go over for the homework. So yeah. So now you're ready for all of homework 2. Okay, any questions about that?
I'm not really sure I understand Fermi's Golden Rule. Can you briefly explain? I don't know, maybe you already said it. I don't really understand the applications of it.
Sure. So the application would be, say you wanted to know if you have a particle in a bound state, say you perturb it with some electromagnetic radiation or some oscillating electric field. You can rewrite the electric field. So the electric field will couple to the energy of the system. Like it will create a perturbation to the energy, like the charge times the electric field or something like that, or that's there'll be some energy term associated with the perturbation, right? So if you have such a perturbation, and you can write it like this, and these A operators would be like, well, it could be some dipole interaction, for instance, with say a magnetic field, an oscillating magnetic field. You could have that. It could be like the Rabi oscillation problem, for instance, right? There we had a harmonic perturbation, and it had this form. The A and A dagger would just be the magnetic moment operators, that go into the energy. So remember that, for we had before for the Rabi oscillations that change in the Hamiltonian was some mu dot delta B, where delta B was the harmonic was an oscillating field. So, okay, so you have a perturbation like that, and you want to know what's, if I have some system in a bound state, what's the probability that this perturbation kicks it out of the bound state and, turns it into a free particle. So you want to know what the transition rate of that happening is per unit time. So then you can, that's what the golden rule formula tells you. It tells you the transition rate is 2 pi over h bar times the matrix element associated with that transition. It's the matrix element of the perturbation squared times just the density of states. This is the number of states at that energy. And it kind of makes sense. Why is it this? Is because if you start with initial energy, EI, then if you kick it, with some h bar omega, then your final kinetic energy, right, is going to be this amount. So you want to know the number of states out there that have that particular kinetic energy. And that's it. That's all it kind of, that's all the ingredients you need to calculate the transition rate for leaving some initial ground state, say, and becoming a free particle. So it just gives you that. Fermi Golden Rule gives you transition rates from some initial state to a final one. It's typically a free particle. So now we're going to talk about what to do more generally when you have a situation like this with a time-dependent perturbation. What's the general kind of scheme for handling such things? And what you want to do is kind of get rid of the dependence on H naught. And we already saw this in the Rabi oscillation picture. We saw this for the Fermi Golden Rule derivation. You want to kind of use as much information that you have about H naught to get rid of any time dependence associated with it. So the general idea is called the moving to the interaction picture. There's the Schrodinger picture where the states evolve, according to Schrodinger's equation. There's the Heisenberg picture where the states are stationary, but you instead interpret the dynamics as just evolving the operators. We kind of saw that implicitly in the first semester, but I didn't, I guess, mention it in particular, but we'll sort of see that now. So the idea is if you have no perturbation, then everything is stationary. And you know that, according to the Schrodinger equation, your state would evolve as follows. So you would have, I'm going to put two arguments here. One is the initial time that you started, and then t is the final time that you're looking at. So this guy would just obey Schrodinger equation, and we can solve it immediately because our unperturbed Hamiltonian is stationary. So we can immediately just exponentiate it, and meaning it's time independent, right? It's just some constant operator. And so we can exponentiate it and get a solution to the state. And of course, we have the initial condition there. It's T naught, T naught there, evaluated like that, just because that's the initial condition. So that's what would happen in the kind of Schrodinger evolution. So what we do now is we define an interaction picture state, which is related to the Schrodinger state as follows. We say this is I for the interaction picture. What we're going to do is take our Schrodinger state, which would be this one, whatever it is now with the perturbation or whatnot. And what we're just going to do is undo the time evolution due to H naught. So it'll be undoing it. It's sort of like evolving it backwards in time back to the initial time T naught. So we take, so if we think about this, what is this? Okay, so if there's no perturbation, then what would this do? We would take this side T naught, which is in the Schrodinger picture, so I can put like a S here for Schrodinger picture. If I stick this expression into here, the two exponentials will cancel, and this interaction picture state will just be completely stationary. It'll just be the initial condition. It won't evolve in time at all. So that's the idea. We define the interaction picture in such a way that whatever this unperturbed Hamiltonian is doing, it doesn't influence the dynamics at all. It's as if it's not doing anything, because if there's no perturbation, we see that the interaction picture is just the initial condition. That's it. It doesn't change, doesn't pick up any phases, nothing. So that's kind of nice. And so what that'll mean is that any time evolution of the interaction picture states, it'll have to depend entirely on the perturbation, right? You know, like the perturbation is the thing that will evolve the state, because the unperturbed part does nothing to it by definition. Similarly, for any interaction picture operators, what we do is we undo the time evolution of H naught. So we take any operator we would normally have in the Schrodinger picture, and we sort of apply the time evolution to it according to the unperturbed Hamiltonian. So any operator that we have in the interaction picture, it looks like this. So yeah, so that's the definition of the interaction picture, and it's just convenient to do this. Why? Because you'll see now that the Schrodinger equation in this interaction picture has a nice form. So you can sort of take these as sort of the definition. This is how you would construct your interaction picture operators and the interaction picture states. You would take the states you normally have according to, that evolve according to Schrodinger's equation, and you would just multiply by this guy. You take any operator you would normally have, and you just sandwich it between these two unitary time evolutions corresponding to the unperturbed Hamiltonian. So that's kind of a definition. So let's see what we can make of it. For instance, let's take time derivative of psi in the interaction picture, and see if we can derive a Schrodinger equation. So that's easy enough to do. The time derivative hits the exponential, gives us a factor of I over h bar h naught, and then we have e to the I over h bar h naught t minus t naught, and then we have psi t naught, the Schrodinger one, and then we have the derivative hitting just the Schrodinger operator, the Schrodinger state. And when it hits the Schrodinger part, it just gives us an I over h bar h psi t naught. So again, when a derivative hits this part, it just gives us the Schrodinger equation. And now this h, of course, is not, this h is the full h because this is now with a perturbation. So this h here, this is h naught plus lambda w is the full Hamiltonian. Oh, and I guess I'm missing a minus sign. So you have these two terms, and now you can start rewriting things so that you get back out the interaction picture state. So the first thing to notice is that if this is h naught plus lambda t, then this term right here, the one with h naught, cancels precisely this term, right? That's kind of how it was constructed anyway. We knew it was going to work this way because we know that the interaction picture is constructed to undo the time evolution of the unperturbed piece. So unsurprisingly, in the Schrodinger equation, that part will just not be there. So you have, so that term cancels and you're left with E over h bar, h naught, t minus t naught. And here you have I over h bar, and the thing you're left with is just a lambda w. And now we're going to stick in the identity as we typically do, which is we put in the minus I over h bar, h naught, t minus t naught, and e. So this is just like multiplying by the identity. This doesn't do anything. Just slightly just putting in identity. And then this guy is just psi t naught in the Schrodinger picture. So, okay, so this is nice because now we have, now we recover the interaction picture stuff. This guy right here, that's just psi t naught interaction picture. And moreover, the W is also something. We can combine this term, and this term. These guys are just lambda W in the interaction picture, right? I just go back here. The interaction picture operator is the same as the original operator, sandwiched between these two exponential factors. The interaction picture state is just the original state, and a Schrodinger picture multiplied by this factor. So all of this reduces to minus I over h bar lambda wi psi t naught interaction picture. So you see in the interaction picture, the Schrodinger equation looks just like the regular Schrodinger equation, except you're evolving with just the perturbation, and the perturbation is also in the interaction picture. So that's important. Wi is not the same as W. Okay. And of course, you have to, your states are going to be your operators. Unlike the Schrodinger picture, the operators will have some time dependence now because they're kind of defined according to this time evolution. So you have to, in the Schrodinger picture, they'd be time independent. This would be like position, momentum, whatever. But in the interaction picture, they pick up a time dependence from these phases, and these unitaries out here. So you have to calculate what that is. So you can do that. You can calculate the time derivative of the interaction picture operator. And so you just use the definition. You sandwich it between the two different exponentials here. Take the time derivative. Of course, you get the time derivative hits the two exponentials. Here, it'll pull down a factor of I over h bar h naught. And then the usual thing is we have to be very careful to make sure we don't pass any operators through each other, so you don't accidentally get zero here. So when the derivative hits the other exponential, you can pass the minus I over h bar through, of course, but you can't pass the h naught past the a. So this becomes a h naught e to the minus I over h bar h naught t minus t 0. So all this is, you have a combination of terms, right, that just gives you the commutator. You've got h naught a and a h naught. And so all of this is just minus I over h bar. And we can write this as the commutator between this sandwiched operator and h naught. And if you look, this is nothing but the interaction picture operator. It's just minus I over h bar. It's the interaction picture A and h naught. So the interaction picture operator obeys the Heisenberg's equation of motion for operators with, instead of the Hamiltonian doing the time evolution, it's just the unperturbed Hamiltonian. So the operators evolve and the states, so the states in the interaction picture evolve with the perturbation and the operators evolve with the unperturbed Hamiltonian. And yeah, and this is a convenient picture for doing time-dependent perturbation theory because it undoes the time evolution due to the unperturbed piece. Okay, so any questions about that? Okay, so we can say a little more. We can, of course, take a basis, which, you know, as usual, we could have it be the eigenstates of h naught. And then our interaction picture states, in terms of this basis, well, they would be, of course, some interaction picture coefficients, time dependent, written, you know, just expanded like this. And the Schrodinger equation for these guys will just be from the Schrodinger equation for the interaction picture is just going to be the matrix elements of the perturbation. And then, of course, we have these exponential factors due to the fact that the W has to be in the interaction picture. So instead of Wi here, I'm going to write the actual perturbation. And then the two exponentials on the side, they will hit these basis vectors and just give us factors of the energy. They'll give us Em minus En. And this is evolved from T naught to T. And of course, there's some initial coefficients there. So, oh, sorry, no, this is just the, sorry, this is the Schrodinger equation for the coefficients. Sorry, not initial ones, just the interaction picture, same as these guys. So that's the differential equation that they satisfy. Again, because W has to be in the interaction picture. Remember, we derived the interaction picture states obey the Schrodinger equation with W in the interaction picture. So these extra exponentials out here, they give us these factors of Em minus En. But you see, it looks very similar to what we did when we did the Fermi's Golden Rule derivation. But now it's just much more general. You see that the general way of thinking about it is that we're moving to the interaction picture. So now what we want to do is actually develop a perturbation theory using W as our perturbation, trying to actually expand our solutions order by order in lambda. And to do that, we want to basically solve the interaction picture Schrodinger equation. So let's think about it. So first of all, let's kind of remember unitary time evolution. We know in general, so without thinking about the interaction picture, we know that in principle, we should be able to calculate the state at time t by evolving your initial state with some unitary operator like that. So that we know that that's just generally how we would go about solving any kind of time-dependent problem. And also that your Schrodinger equation, of course, it's with a time-dependent Hamiltonian looks like this. And moreover, if you recall back from the first semester, these unitaries, they were actually just related to this Hamiltonian as follows. This is actually IH bar dt u. Of course, it makes sense. I just substituted in this. So this, so you can see here that, so the next step what we can do is, you'll see in a moment, it should be familiar to you what's going to happen. So this is psi at time t. We can, of course, undo the evolution of the state by applying the Hermitian conjugate of the unitary operation, because we know that taking the Hermitian conjugate will invert the time evolution. And so we can actually write this as, for instance, we can write the psi t naught. What is this thing? We could take the state at time t and just invert the time evolution back to time t naught. And so if we do that and we plug this back into here, then we'll see that we have the following relationship, right? That I h bar partial t acting on u times u dagger has to be equal to just h. And moreover, we can act with u on both sides. So I h bar partial t u is equal to h u. It's just the relationship between unitary time evolution and the Hamiltonian. We looked at this kind of relationship before, actually, in the first semester. We basically derived this. But the reason I am showing you this is because you see the unitary time evolution operator u is not like a standard operator in that its equation of motion is not the same as you would expect for operator, like a Heisenberg type equation, right? This is what we had for like a Heisenberg picture operator. In the unitary time evolution, its equation of motion looks more like a Schrodinger equation, right? So you can show then, similarly, that in the interaction picture, if we take, u of I, in the interaction picture, it's not like a regular operator where you sandwich it between the two phase factors. It behaves more like a state. And so in the interaction picture, this is just something important to keep in mind. In the interaction picture, the unitary time evolution transforms like this. It transforms to this. So this is the regular time evolution you would have, and to move it to the Schrodinger picture, you'd multiply by this phase factor out front, just like we did for the states. So that's another important piece to kind of keep in mind. So here, you see, I said the interaction picture states transform like this, and the operators transform like this. And there's a little bit of a caveat in that the unitary time evolution also transforms like the states. So this is, and not like the operators. Just something to keep in mind. So I'm going to put it in small lettering there. Just something to keep in mind, but you can, of course, derive all of it by thinking about what the relationship is between the Hamiltonian and the unitary. They're related, of course. And moreover, you can get from that directly by applying a time derivative, just as before, that the equivalent Schrodinger equation for u in the interaction picture now is just that it obeys the Schrodinger equation, but with the perturbation only. So this is the interaction picture version of the equation for u. And again, remember here in the setting, it's always like that. Okay, so now we have our evolution operator equation in the interaction picture. And the reason this is useful is because we can actually use this equation. We can actually solve for u of I. We can sort of formally integrate this equation. And the integration of this equation gives you an integral equation that doesn't seem obviously better. But because we're going to assume lambda is small, right, then it's going to be okay. We'll be able to solve it perturbatively. See, if lambda is 0, then what does this tell you? It tells you that in the interaction picture, the evolution operator, the unitary, doesn't change in time. It's just stationary, just a constant operator. And so maybe we'll be able to expand in lambda and see what happens. So, okay, so what we can do is we can integrate this equation. You can, of course, do this with any Schrodinger equation. It's just that the equation you get is typically useless because, well, it's you can't solve it either. If you can't solve this equation, then you can't solve its integrated form. But okay, let's integrate it. And what we'd find is that the U interaction picture operator is equal to the identity minus, and this is, so minus a lambda I over h bar integral from your initial condition out to t. And of course, this identity is just the initial condition. It's then the integral dt of wi, so of course dt prime ui t prime t naught. So there we go. This is just integrating up this differential equation. We just put the I over h bar on the other side. We integrate both sides, and here we'll get ui minus the identity because it's the initial condition. And then we're left with just this integral minus lambda times I over h bar integral from t naught to t of just this side, which is wi and ui. So it's just it's like rewriting the equation. You haven't done anything. All you've done is just sort of integrate both sides. So you can of course do that with any Schrodinger equation. It's just usually it's completely useless, right? Because you have a ui over here and a ui over here. So this is another equation you can't solve. So that's not great. But the idea is that lambda is small. So we might be able to just solve it perturbatively, order by order in lambda. So the thing to notice is to order. So now we do the time-dependent perturbation theory. And to 0th order, of course, the interaction picture U is just the identity. As promised, if there's no perturbation, then in the interaction picture, the state just doesn't change. It's just the initial state forever. To next order, what we do is we just say, well, fine. We're going to have our expression, and instead of this is all stuff we have, but instead of substituting in u of I, we're just going to use the previous order, because we know any higher order corrections will give us something that's order lambda squared. So it'd be of higher order. So we just put in the identity here instead, which of course is just 1. So this would be the first order correction due to the perturbation. You see, it was just this integral of just the perturbation in the interaction picture. And we can keep going. Of course, we can, at lambda squared, we would put in this entire expression into our integral. And so in general, up to order. So, okay, let's do the next step, I guess. Let's do. So we have our first two corrections, identity minus h bar t naught t prime. And then we're going to have a double integral, right? So there'll be two factors of these lambda minus I over h bars. And now we have an integral from t naught to t dt prime wi t prime. And instead of u of I, we have to put in this guy, which is another integral. And now we're going to And remember, this is all the way up to t prime. So this integral goes from t naught to t prime, which is the variable of integration here. Because remember, we have to substitute in for u interaction picture evaluated at t prime. So we have to go from t naught to t prime. So now we have to introduce another integration variable, t double prime, and this is going to be omega I t double prime. And now it's just the identity, because anything of higher order will be lambda cubed. And so you can keep going with this. You can just keep back substituting in the previous order and just keep going to higher and higher orders in lambda. And what's kind of inconvenient about all this is that each time you do that, you get these iterated integrals. You always get something like from t naught to t of wi, and then you get from t naught to t prime, where t prime has to be less than t. Another wi, you do it again, t naught to t double prime, and now you have a whole chain of integrations where t double prime is less than t prime is less than t. You keep getting these iterated integrals, and that's quite annoying because it means we have to do them one at a time. And so you first do the inner one and this one and this one, and that's very annoying. We don't want to deal with that. So we want to rewrite this in such a way that we can pull out all the integrations. But to do that, you have to be very careful because these w's don't necessarily commute with each other if they're at different times. If they're at the same time, of course, that's the same operator. And, if we have something like this, of course, that's the same operator, and operator commutes with itself. But if they're different times, then it's not necessarily true that you can just slide them past each other because they're operators. So in general, at different times, they, might not commute because they're different. So we have to be careful. So what we do is we introduce the concept of time ordering. And this is a way of keeping track this idea that sometimes they won't commute. But before I move on, are there any questions about this basic setup of what I'm doing here? This is the general solution. At each order, I just plug in, instead of u of I here, I plug in the previous order. So first, nothing, say identity plus 0. Next step, identity minus this integral. And then I substitute, instead of ui, I plug in this guy, the I. Next step, I do identity minus this guy. Instead of ui, I put in this previous step. So it would be the identity, which just gives me this integral, minus lambda I over h bar. It gives me another factor of, minus lambda I over h bar. It's this integral, and now it's this integration. But now this integration only goes up to t prime, right? Because I'm evaluating it at t prime. So you have this iterated integral. And then you just can keep going with that. Wait, any questions about that? Okay, so in order to simplify these integrals and not have them depend on each other, where, like, again, this would be like, this is over dt. Oh, sorry, this is dt prime t. Oh, you want to avoid this iterative thing where the limit here depends on this variable of integration. So to avoid that, we introduce this concept of time ordering, which says that if it's a function of products of operators at different times. These are just some operators. Of course, they're going to be our W's, but just some operators that are time dependent. And the time ordering basically just puts them in the right order. If t is bigger than t prime, then you stay the same. So we want the later times to come first. And if not, then you just reverse their order. And this ensures that the operators stay in the correct order, with the later ones coming first with the later times. See, this omega I, this t double prime has to be less than this variable of integration here, or here, this t double prime has to be less than t prime, which is what this as an operator. This operator is a function of t prime, and this t double prime has to be less than t prime. So it has to be time ordered that way. This operator has to come before this one. So, or sorry, I guess I have it backwards here. Oh no, this is right. Yeah, so this operator, the t w at t prime, right? The t prime has to be bigger than t double prime. Just from here. So we want to make sure the w's stay in the same order. So we want the latest one to come first with a bigger time argument. So, okay, so let me just show you how that works then for this integral. Say you have this double integral from t naught to t dt prime wi t prime t naught to t prime. We can write this now as the following. We can write it as the integral from t naught up to t for both integrations at the price of introducing a time ordering such that this wi, the first one, always comes sort of before the other one. And if you think about it, if you think about the integration plane, so this is the t double prime and this is t prime. We're integrating t prime from 0 up to t, but t double prime or from t naught rather, from t naught to t, but t double prime just goes from t naught out up to t prime. So this is the kind of area of integration that we're covering in terms of the t prime and t double prime variables. Now here, we're going to allow t prime and t double prime to both go from 0 to t, or from t naught to t, right? And so what we've done is, this is the original integration. We're allowing for the integral to hit places here where t double prime is bigger than t prime. And that's bad because of this commutation issue. So to fix that, we introduce a time ordering to make sure that these operators are always written in such a way that the latest time one comes first. And if we do that, then we're allowed to extend this integration region, because then really this integral over this upper portion here will be the same as the integral over the bottom portion. They'll be equal integrals because of the fixing due to the time ordering. And the only price we pay for introducing more, for introducing integration over this part is just a factor of 2, right? To divide by 2 because we're integrating over twice the area, and this integral over this bottom part is equal to the integral over the top part, as long as we properly make sure that the operators are always in the right order. So the time ordering allows us to do this and change these variables of integration to cover the full range now. And now this just becomes a simple double integral, and we don't have to do this iterated integration business anymore. And this extends to arbitrary products of W's. As long as we make sure that they're always in the right order, then we can extend our region of integration to cover all possible times, because the integrals will be just equivalent in the different regions. So the general formula then is, if you have any integral, any set of iterated integrals, let me call these T1 now, up to T1, and you have dt2, and so on, all the way out to T0 to T to some n minus 1, dtn, and then you have your products of the operators like this. Well, then I can play the same trick of introducing a time ordering, and you can convince yourself that the amount by which you expand your region of integration is n factorial. So here it was by an amount 2. In general, it's going to be by an amount n factorial, where n is the number of integrations that you have. And you can reduce all of these integrals to just integrations from T0 up to T. A bunch of them, all of them the same. Like that. And the only price that you pay for doing that is now you need a time ordering of the product of all of these interaction picture perturbation guys. Yeah, any questions about that? The time ordering? It's a pretty important concept. It's an important concept because we'll now actually be able to sum up this perturbation theory to all orders. We can do, because there's a pattern here, each time you go to the next order, you just get another iterated integral. And the only issue is that they're these nested integrals, but if you can get rid of the nesting, then at each order, you will just pop in another integral from T0 to T. And that's fine, we can do that. So this is what I'll leave you with, is that now you can do perturbation to all orders, namely that the interaction picture evolution operator is a sum over all the terms in your perturbation theory. Each time you get a new factor of lambda I over h bar. So there's a bunch of those factors. Then each time you go to another order in the perturbation theory, you pick up an integral. The 0th order has no integrals. That's why you sort of start with T1 here, but the n equals 0 term is just the identity. you pick up a bunch of these integrals, n of them, and oh, sorry. And so now we're doing the, sorry, this should be up to t. It's the same integral. So we're doing the time ordering trick. And this is going to be the time ordered product of a bunch of these w's. All the way up to Tn. And now this is great because we can actually exchange the integrations with the time ordering. Integrations are just sums, right? So we're allowed to exchange the time ordering with the integrations. Nothing really preventing us from doing that. And moreover, because the integrals are no longer dependent on each other, each integral would just go with its corresponding w. So this becomes, I can pull out the time ordering just out here because everything else is just a sum. And you're left with this minus lambda I. Oh, and of course I'm forgetting something. I'm forgetting the 1 over n factorial from up here. Lambda I over h bar and 1 over n factorial. And now what I have here, right, is just a product of a bunch of integrals that all look the same. It's the integral from t naught to t of dt1, say, omega I t1. And there's n of them. They're all the same if I pull this time ordered product out. And if I look carefully at this, this is nothing but the Taylor series for an exponential. So this is the time ordered operator exponential minus lambda I over h bar integral from t naught to t dt. Let's call it t prime now. I t prime. And this is the exact sort of solution for the interaction picture evolution operator. But the time ordering is critical. It's really important. So it's not, the time ordering makes life difficult. But we'll leave it here for now because it's sort of the end of the class, and we'll talk more about it, what we can use this for later.